It began with the forging of the great power supplies. 2 were given to the riders, those that hover above the land and those that carve through its paths. 4 were given to the USB devices, one of which itself became a legend of epic proportion. 1 of great might was given to the battery boxes, who above all else desire power. Within these power supplies was bound the strength and will to govern the voltage needed by each device. But they were all of them deceived, for another power supply was made. In the land of Amazon, in the fires of inexpensive replacement parts, the Dark Lord of Buy Now brought forth in secret a master power supply set to replace all others. And into this power supply, many holes were drilled to increase the power it could provide from half its advertised rating to a somewhat better 3/4 of its advertised rating. 1 power supply to rule them all. I hope you enjoyed seeing this video about my 1 charger to rule them all. Hopefully it was informative. Hopefully it showed something kind of cool that you might like to try yourself, seeing how many different devices you can power from 1 charger. It's not entirely practical because obviously I really at this point have just as many dongles and adapters and converters to go along with it as I would if I just had multiple other chargers, but I still think it's kind of a cool project nonetheless. So I want to answer a few questions that you might have about this project and about the things that I showed in this video. One question you might have is, how does this MacBook adapter work? Well, this MacBook adapter is just an XT60 connector, which goes straight to the barrel jack, connected to the old-fashioned, I think, MagSafe 1 MagSafe connector. And as you saw in the video, there's a MagSafe 2 adapter as well for newer laptops. There's no active electronics or converters in this. It takes 19 volts in from the laptop charger, so it really is only compatible with MacBooks that are capable of running on 19 volts, which most of them are, but some of the older ones use 16 volts, so you'll want to be careful with that if you are going to use an adapter like this.
The second question you might have relating to that is, even though I only showed my phone being charged by this ElectJet branded USB Type-C to MagSafe adapter, can this support other USB Type-C functions? Absolutely. This thing actually is rated to operate up to 45 watts in the highest mode for the 20 volt 2.25 amp USB Type-C standard. It doesn't go all the way up to the 100 watt fast charge, but at 45 watts you can power just about any modern USB Type-C device with reasonable satisfaction. Another question you might have is, well, what is in the cardboard box? And the answer is just two boost converters, two of those D-Rock converters. One of them is set to 42 volts for a 10S lithium battery pack charging setting, and the output current is set to 1.5 amps, so that the input current drawn is about 3.5 amps from the 19 volt supply. Interestingly enough, this power supply will provide even more than the 4.62 amps it's rated. I've actually seen it run up to 5 amps without a problem in the short term, but even at just 3.5 amps, the surface of the charger clocks in at over 90 degrees Celsius, which means the internal components are well over 100 C. So it's definitely a good thing to keep this below about 3.5 amps, and as you saw in the beginning of the video, I drilled holes in it to basically keep it from blowing its capacitors out, which did happen the first time I used it for a prolonged amount of time. I had to replace them with some JW Co capacitors, and now it's been working great. So with that, you might ask, well, what's the second boost converter in here for? And furthermore, why did I choose this particular charger, seeing as it's noisy and seems to have some issues with reliability? Well, the second boost converter in this box is actually a step-up converter from the battery voltage at the 42 volt input to a 60 volt DC output, which I've connected to this oven or stove style 120 volt plug. It's a 60 volt DC output, and you might say, well, that's not enough to run pretty much anything. Well, this charger will actually run quite happily at 60 volts DC. The input stage will get slightly hotter and it will drop out at a lower current demand, so this is really only good for running maybe 50 or 60 watts when it's connected to this, but it's plenty to run my laptop, and I use it almost every week to charge my laptop using that 42 volt battery from the Meepo skateboard that I had. And it works great for that. So I really selected this not only because of its low cost and the fact that I already had it from another project, but also because of that low input voltage cutoff that allows me to operate it from other batteries. Likewise, I am also able to get it to operate off of that large e-bike battery that I showed, although that one does actually require it to be sort of kick-started by a higher voltage supply to get it going, and then you can just really fast kind of jump it over to the battery and it'll keep going on the battery. So highly versatile in terms of input voltage, and obviously going in the other direction, it supports all the way up to 240 volts AC, and the components in it are all rated for up to 400 volts, so presumably you could run this directly off, say, an EV battery if maybe you had a little bit of voltage drop in series with it. So very versatile input voltage range. It outputs 19 volts, which of course is what my laptop uses, but also is a fairly versatile voltage for powering all kinds of DC to DC converters. So hopefully that answered a lot of your questions, and hopefully you enjoyed watching this video. Thanks for watching. And I know what you were all thinking, don't turn it on, take it apart. And of course, it's pretty easy to take this apart. I have had it apart a few times before. You just pry at it a little bit, it'll snap right open, and we can take a look at what's in it. So hopefully if we can get all this plastic off, we'll see it's a pretty standard switched mode power supply. You'll see a couple of little modifications that I did. One modification that I applied was I added some of these nylock nuts to the switching and rectifier diode mounts to the little heat sinks, because over time I found that they were getting loose on their own because of thermal expansion. I also added a little crowbar circuit. This is just a Zener diode with a BJT on it. And what that does is, if in the event that there's a voltage spike at the output, this clamps that to about 22 volts to try to just make an effort to protect the device connected to it. Makes it a little less likely to blow anything out if something goes wrong. As I mentioned, the original capacitors failed because the diode pulled off the heatsink and then went intrinsic and shorted AC from the transformer onto the caps and blew them out. So I put these JW Co non-low ESR. These are actually regular JW Co capacitors. Probably should have put low ESR capacitors in, but they've been in for almost a year without trouble, so JW Co makes some of the best low-end capacitors you can get. They're not anywhere near as good as the Nikon or Nippon Chemicon or Panasonic capacitors, but they're certainly pretty robust in terms of the lower end capacitors. That little guy there is kind of important. That is the enumerator chip. It's a little 3-pin, looks like a transistor, but what it does is it actually generates the center pin signal for the barrel jack that allows Dell computers to operate with this power supply. We've got a little bit of interference suppression. This is most likely a Class Y capacitor, although it could possibly not be a Class Y. I certainly wouldn't necessarily trust this thing with my life. I'm not going to take a bath with the device I'm using on it, but I have tested its isolation and it holds up to a 1 kV high pot, so it's not too bad. There's the switching transformer, reasonable size. It's not huge, but this is only realistically a 65 watt charger, even though it's rated as a 90. Main input side of things, we've got a big can. This is a pretty standard 400 volt capacitor. It does have a fuse on the input. However, one of the things it's definitely lacking is inrush suppression, as there's a bridge rectifier going straight from the input to the large capacitor with no power factor correction or NTC thermistor, hence the large sparking and popping that you get when you plug this into the wall. That could definitely be an issue if you are plugging this into a really rigid power source like an electric vehicle battery, so a little inrush mitigation wouldn't hurt. That being said, it's not really that big of an issue because the line cord it came with is one of those super flimsy, probably 3-strand of aluminum, copper-clad aluminum type cables. So honestly, there's probably a couple of ohms of resistance in this cable alone, which probably will save those diodes from getting blown by the inrush anyway. So it kind of is a self-correcting problem in that respect. Having a look at the bottom, just some basic components. It's your usual switch mode power supply. You've got your single chip here for regulating all on the primary side, a couple of rectifiers for the basically the feedback and then the supply from the transformer to power the bootstrap circuit. And then on the other side, looks like we've got a couple of, basically regulating resistors. We've got the output of our Schottky diode for our rectifier and the place where I attached the crowbar circuit. Now there is an optocoupler in here, so it actually has extremely good regulation under load. Regardless of the load, it pretty much puts out 19.5 pretty well straight on. Not great ripple rejection. I didn't show it on the scope in this video, but you're getting around between 200 and 500 millivolts of ripple, which is a little bit much, but nothing I've plugged in has complained about it. One thing to note that might be a safety thing to keep in mind, when I first got it, the secondary heatsink and this primary heatsink were actually touching. I corrected that problem by just bending this secondary heatsink over a little bit. I don't think these heatsinks are actually connected together to the actual circuitry. The primary one has a little tiny gap there on the single-sided board, so I don't think it's actually grounded to anything. These are also insulated TO220 packages, so they're not directly bolted to the heatsinks either. And the secondary heatsink also appears to be isolated, so even if they were touching, it really wouldn't be a problem, but I felt a little more comfortable just bending that back. So hopefully you enjoyed this video. Hopefully you enjoyed this little teardown of this one power supply to rule them all, and I look forward to seeing you in the next video. Thanks for watching Dielectric Videos, and I will see you next time.